Hi, my name is Charlotte Kramer, and today I will be presenting to you my paper titled Notes on Spaceflight. So in this presentation, I hope to give you a brief synopsis of the paper as a whole, starting from its introduction to an analysis of its conclusions. So let's start at the start, my research question. My research question is, what is the relationship between the periapsis length and the change in velocity required to escape a celestial body's gravitational field by a rocket when using the Oberth effect? So this paper explores the effects of gravity on low orbital delta V maneuvers, namely how the distance from a celestial body impacts the amount of delta V needed to reach escape velocity. The paper's findings are logically sound, coming to the conclusion that deeper falls into gravity wells will allow for less delta V needed to escape. So I will start by introducing to you the key variables. The periapsis of an elliptical orbit is defined as the point which is closest to the surface of the celestial body it is orbiting about. It is also the point at which the rocket has a highest velocity, as is shown by Kepler's laws of planetary motion. When speaking of a change in velocity, or delta V, this paper is referencing delta V maneuvers, or burns, during which a rocket accelerates propellant out to its exhaust, producing thrust. So from the beginning, I hypothesized that there would be a positive correlation between the length of the periapsis and the amount of delta V needed to reach escape velocity by a rocket when using the Oberth effect. So at this point, you're probably wondering, what is the Oberth effect? That's a really good question. The Oberth effect is a rocketry phenomenon relating to delta V maneuvers, which was first suggested by Hermann Oberth, a German scientist and the namesake of the effect, in his 1929 paper titled Ways to Spaceflight, hence my paper's name, Notes on Spaceflight. So here we have some of the calculations first done by Hermann Oberth, showing that the specific kinetic energy of a rocket increases at higher initial velocities, meaning that more kinetic energy is gained for the same amount of delta V at higher initial velocities. We can now begin deriving the specific relationship between the two variables. So to do this, I first had to define escape velocity. I decided to integrate the force of gravity from the periapsis distance to infinity to find the work done by the rocket needing to escape. Equating this subsequently to the kinetic energy needed to escape, a function of escape velocity, I was able to rearrange to solve for the escape velocity. However, that was not all. I then had to take into account the effect of the Oberth effect. So to do this, I used two principles of physics. First, the conservation of angular and specific momentum. As both are conserved in an elliptical orbit, I was able to equate the velocity at one point in the elliptical orbit, the apoapsis, to the velocity at another point in the elliptical orbit, namely the periapsis. I then used the conservation of total energy to rearrange this equation to solve for the velocity at the periapsis. After this, it was a very simple trick of finding the difference between the velocity at the periapsis and the escape velocity needed to escape at that point. So therefore, delta V can be defined as the equation above. When graphing these findings using MATLAB, we can indeed see a positive correlation between the two variables, as I hypothesized. However, to ensure that there was merit to my theoretical findings and to all of the math that you saw before, I had to do an experiment. As I can obviously not launch rockets into orbit yet, it's a little difficult right now, I decided to use a rocketry simulator. So there are a lot more steps, but I simplified it into two. So starting from an elliptical orbit, a periapsis length is reached using a retrograde burn. Note that this periapsis must be above the atmospheric limit. Once at the periapsis, a prograde burn is performed until escape velocity is reached, as is shown by the rocketry simulator. The results are then recorded and graphed. So when graphing the results against the theoretically derived relationship, a very, very high correlation between the two is found, with over 50% of the experimental data going through the theoretically derived trend line, and the rest not being far off. This does bode well for the paper as a whole and gives the results significant merit. However, there are severe limitations. Mass changes were not taken into account, and rockets lose significant mass while accelerating propellant out of their exhaust, which wasn't at all accounted for. Furthermore, the simulator was done on an incredibly small scale, in fact, 1/10 of the size of our solar system, so perhaps the experimental results aren't realistically applicable at larger scales. Nevertheless, the conclusions remain absolute, with a theoretical relationship found and experimental results which strongly reflect it. It can be said with a degree of certainty that this is a relationship between delta V and periapsis length. Following this paper, I would like to do some further research. First, investigating changes in mass, so taking into account the significant changes in mass that rockets undergo. Secondly, investigating at larger scales, so therefore using a proper rocketry simulator and perhaps more trials to give the experimental results more merit. And lastly, by finding specific fuel consumption and efficiency gains using the Oberth Effect. I think the Oberth Effect has a lot of potential for the future of sustainable long-term spaceflight, which will be a problem and a challenge for my generation, I'm sure. So that is it. Thank you so much for listening. Yeah.
Okay, such a fascinating topic. Thank you for coming here. Can you tell us a bit more about what inspired you to delve into that project, basically?
Yeah, so I have been interested in physics for a while, and for me, it was always this idea of, more. Like, we had just Europe, and then we had boats, and we had Europe and America, and then we have planes, and now, I go to Florida every single summer, and this idea of we make something new, and then there's more. And then I think a couple of years ago, I was in the middle of nowhere, and I looked up at the sky, and I saw space, and there's so much more. So I started reading, Stephen Hawking's A Brief History of Time and all of these books on theoretical physics and space exploration and stuff. And I had this moment of realization, that's what I want to do. I want to bring, us a little bit closer to space. So at school, I was reading something and I came across the Oberth Effect. And it was talking about how to promote sort of long-term spaceflight and get us, further and further away from our planet and closer to, the reaches of outer space. So I did some research and I found that there wasn't an awful lot on the topic, or at least not an awful lot that I could understand. So I thought, that's what I'll do. I'll try to, show the maths behind the physics, behind the system. I will explain to people like me, or even, to university students, how that works, and I'll find a relationship between these two super important things.
Okay, we see that there are huge developments at the moment, like for space flights, and they are developing new technology, trying to push rockets by lasers, for example, and it's really developing. It means that when you're going to leave university, you're going to be at the heart of probably the next space flight to Mars. How do you feel about that?
Really good, really, really good. So I'm about to go off to university, and every single day in the news I read about something that Luxembourg has done for space, or I met an alumni last year or something who's working at a space company in Luxembourg right now, and he was saying, every single day I see a new challenge. And when I graduated from Luxembourg, I thought, I'm never coming back here. And now all of a sudden we see so much space, even in little old Luxembourg. I mean, who knows what's out there? It'll be, I'm super excited.
Do you have any particular field that particularly interests you? Like you mentioned, your early interest, but where would you see yourself in 10 years, for example, ideally?
In 10 years?
On Mars?
Fingers crossed. I wouldn't say no. If they invite me to Mars, for sure.
Okay.
I think for a while I want to stay on Earth. Maybe talk about launching mechanisms and how we can sort of best sustain long-term flight. In the end, I think moving humans off Earth is going to be a big thing. And it's something that I'm looking forward to. I think we're going to be facing all of these different challenges, not even just in the realm of physics and maths, but in psychology and biology, and how do we pick up a species and move it to a different planet. So I'm super excited for the new space age, and you're right, we're going to be seeing so many different things every single day.
Yeah. What challenges did you come across for this project?
I think finding resources was probably the hardest. A lot of the stuff is, really niche research papers that aren't super applicable outside. And when I wrote the project, I still hadn't done an awful lot of research on the specific physics of orbital mechanics. So for me, I was reading books and teaching myself really basic principles to do this fairly complex topic. So yeah, I think starting up the project and then also being able to sort of compare the results quite accurately. So like I said in my presentation, I can't launch anything into space. So I really had this sort of idea of how do I make an experiment out of this? How do I do that? So eventually I found a rocketry simulator, but even then it was too small and I wasn't happy with it. But I think it worked out okay in the end.
You should totally connect with the kid earlier who actually made rockets in his garden.
Yeah. To keep building them and so on.
Yeah.
Did you get in touch? Did you, in the things that you read and so on, did you, with the names that you found, did you get in touch with any of the experts?
No. Personally, no. But I have been able to reach out through LinkedIn, especially to a lot of heads in industry, and I've spoken to them about my project, and I've had them even look at it, which was really, really exciting. Sort of being able to share my passion with someone that's equally passionate. It was jarring for me because all of my classmates look at it and they're like, "You're crazy." Yeah.
We really can feel your enthusiasm at least. Yeah. Really, it's.
And which bit was more nerve-wracking, speaking to those people, or doing the talk, doing your talk just now, or talking to the jury?
I think doing my presentation was probably the most nerve-wracking for me. I just had an exam fairly recently, so I walked into the presentation still thinking about my exam and stuff. But yeah, I think the presentation was jarring, and then being able to talk to the jury, I sort of felt that enthusiasm for space that I think everyone at the moment has. It's weird to see it. Everyone's excited for space. So, yeah.
Well, many thanks for communicating this enthusiasm to us, at least. Yeah.
Do you have any last words of encouragement to other participants in the contest this year, or anyone who might want to participate in the future?
Go for it, I think. Definitely. When I heard all of this stuff, you have to make a presentation and then do this and then do that, I thought really, oh no, what have I done? But being able to be here and talk to everyone and sort of present the stuff that I love and the stuff that I want to do as a young person and have my voice heard, I think that's so, so powerful. So just do it. Yeah, go for it.
Because it's important to precise that you have a high degree of freedom in the choice of your topic, and
yeah. You can do whatever you want, really. You can even do rocket science.
Cool. Thank you very much for your time, and all the best for Sunday, which is another hurdle. Well, not a hurdle, but another bit of the contest.
Everyone's a winner.